Oh, hey there. This is going to be epic. What if I were to tell you that pi has a pattern? Oh, it does. And we're going to see how we can use our understanding now of power series to prove it. Pattern's actually really nice. Let's get there. Let's do it together. I'm psyched. So, I'm going to lead you to it. First, we're going to write the first four non-zero terms and the general term for the Taylor series for arctan x about x equals 0. Now you might think, yeah, I don't want to take a lot of derivatives of this in the Taylor series process, though you could, and that would work. So I'm going to actually use what we just went over in the previous video, in video 3 of this chapter, or this lesson, if you will. I'm going to take a derivative first. The derivative of arctan, for those of you that forget, way back in chapter 5, is 1 over 1 plus x squared. Now, why is that important? That's important because that's in the format of a over 1 minus r. In fact, a little bit of manipulation is going to see that we have it centered at about 0. It's a much easier way to go about it, using the sum of a geometric series. 1 minus a minus x squared gets us there. Oh, so that's a, that's 1, that's minus r. So I've got a equals 1, r is equal to minus x squared. So in typical form, I've got n equal to 0 to infinity of a r to the n, and that's equal to n equal to 0 to infinity of a is just 1, so we'll just leave it out, minus x squared to the n. So that's minus x squared to the n, or minus 1 to the n times x to the 2n, however you want to write it. Now, this is going to be the first four non-zero terms in the general term of the derivative. We'll have to integrate this to get back to arctan. Let's see what we got. So, first of all, let's expand this out. When I plug in 0, I get 1. I'm going to multiply by minus x squared each time. So I get minus x squared times minus x squared is x to the 4th times minus x squared is minus x to the 6th. We only need the first four terms there, plus dot dot dot, plus this was, again, however you want to see it, already as negative 1 to the n. That's that negative 1 to the n, x to the 2n, 2 times n. And then it keeps going, going, and going. So that's our series for the derivative. This is what g prime of x, which is equal to 1 over x squared, 1 over 1 plus x squared, is equal to. So now the integral of g prime of x, dx, equals g of x. Right? The integral of that derivative would get us back to what we want, which is arctan. So we're going to integrate this. Now keep in mind here that the interval of convergence, the absolute value of r is equal to the absolute value of minus x squared, is less than 1. When you simplify that out, x would have to be between 1 and negative 1. You can test your endpoints, except you don't need to because it's geometric. All right, so let's check this out. Now we integrate this, and this is what is so fascinating about all of this. It's meant to be, and you'll see this in a second. Anyway, we integrate this, we get x, very easy to integrate actually, minus x cubed over 3, plus x to the 5th over 5, minus x to the 7th over 7, just straight up integration of a polynomial, plus, we want the general term, that's going to be negative 1 to the n, x to the 2n plus 1, all over 2n plus 1, and it keeps going on and on. That's the first four non-zero terms, 1, 2, 3, 4, and the general term for the Taylor series for arctan about x equals 0. So this is arctan x. Now here's the important part. Our interval of convergence for the derivative was negative 1 to 1, not including either of those endpoints. I want to point out that at x equal to 1, if we were to plug in x equal to 1 and do a test of this, if you plug in 1, you would get 1 minus 1 over 3 plus 1/5 minus 1/7 plus dot 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 plus negative 1 to the n all over 2n plus 1. And that is a converging alternating series. So this series converges at x equals 1. Why is that important? Because we need that endpoint to prove that pi has a pattern. Just barely by the skin of our teeth do we converge. It doesn't even converge at negative 1, I don't believe. And that to me is crazy. Or it might converge at negative 1 as well. I haven't checked it, but it does converge at 1. It does converge at 1. Wow. Really, really close. That thing came to not working out. In fact, I'm doing it in my head right now. It would converge at negative 1 as well. Because if you plugged in negative 1 into here, you'd get a negative 1 to the 2n plus 1 ends up being negative 1 to the 3n plus 1. And that does end up alternating, right? You end up going 1, and then 4, and then 7, so we end up alternating. So we barely converge at the endpoints. Use the first 4 non-zero terms of the power series to approximate arctan of 1. Show the error is less than 13/100ths. Okay, so the arctan of 1 is therefore approximately the first 4 non-zero terms. So that's this, 1 minus 1/3 plus 1/5 minus 1/7, right? That's when we plugged in x equal to 1. That's plugging in 1 here. The next term is going to be 1/9. So that's the first 4 non-zero terms. Now we know that arctan of 1, if you're saying the tangent of what? Well, we'll go to that in a little bit. I was going to give you, I don't want to give away the story yet. Oh, no. I'll just leave it at that. So what's the error? Since this is an alternating series that converges because its terms decrease in absolute value to 0, the error is at most the first ignored term. So the first ignored term, the absolute value of that, is the absolute value of 1/9. It's the first ignored term, which is less than 13/100ths, right? It absolutely is less than 13/100ths. And you might be like, how do you know that? Well, this guy right here, 1/9 is 0.111111111, right? Which is it's a little bit shy of 13/100ths, or 0.13. This is 0.11111. So it's less than 0.13. Okay, so did some of the justification out loud there. Now let's use our result. So what we just found out is we have that the arctan of 1, going to the last page, is this pattern right here. So the arctan of 1 is equal to 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus ... plus, and then we just use our pattern here. Remember that all we're doing is plugging in 1 into this, so that becomes 1, -1 to the n over 2n plus 1. So -1 to the n all over 2n plus 1, and so on and so forth. That is the arctan of 1. How do we know it converges to that? Because we showed that x equals 1 is on the interval of convergence. So this converges to the arctan of 1. What's the arctan of 1? Well, that's like saying the tangent of what is equal to 1. And that is the tangent of pi over 4 is equal to 1. So what that means is the arctangent of 1, which is equal to this, is equal to pi over 4. Why is that important? Remember what we want to show, that pi has a pattern. So you now have an equation where we're right on the doorstep. You've got this infinite series, which converges. We know it converges to pi over 4, right? Because that's what arctan of 1 is equal to. And pi over 4 is equal to this. It's an equation. To get pi, I multiply both sides by 4. So I would get 4 times 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus ... plus -1 to the n all over 2n plus 1. And it keeps on going. And that is pi. That's it. You might be like, what? That's pi? Yeah. Pi is made up of a simple pattern. Alternating signs of fractions where the denominator just goes up by odd numbers, multiplied by 4. And the farther out you go, the closer you get to the true value of pi. So how do supercomputers compute more and more decimals of pi? There's your algorithm right there. So anyone that ever told you patterns don't exist in pi, they're incorrect. The decimals have no discernible pattern, just looking at them. But they're made with an actual very simple pattern. One that we can use a power series to get to. Oh, awesome, right? I think so too. I'll see you in the next video, but until then, think about what just happened here. I know I'm going to. All right, that was corny. But seriously, think about it a bit. It's pretty sweet. Until next time, peace.